Archaeologists of the future will trade their shovels for spacesuits. They will not dig in ancient dirt but float in silent orbits, scanning the rust-colored plains of Mars and the dark, rocky fragments of the asteroid belt. Their mission is not to uncover our past, but to search for relics of civilizations that are not our own. This is the thrilling frontier of astroarchaeology, a new science that blends cutting-edge technology with cosmic detective work. It is the deliberate search for alien artifacts right here in our own solar system. By the end of this exploration, you will understand how this search is already beginning and what a single discovery would mean for every person on Earth. We will examine the strange, silent places where evidence might be hidden and the incredible machines that will do the digging. What if our moon holds a perfectly preserved artifact billions of years old? Could a derelict probe be drifting among the asteroids waiting to be found? This journey will take us from theoretical foundations to mind-bending technologies, all leading to a single possibility that could shatter our cosmic loneliness. Are you ready to see the solar system not as a collection of planets, but as the greatest archaeological site imaginable? This search for cosmic artifacts is not science fiction. It is the foundation of a real and emerging field called astroarchaeology. At its core, astroarchaeology is the scientific hunt for physical evidence of technology built by something other than humanity. Its target is not a radio signal from a distant star, but a silent, solid object hiding somewhere in our own celestial backyard. This is a crucial distinction from traditional SETI, the search for extraterrestrial intelligence, which has spent decades listening for whispers across the galaxy. SETI listens for a conversation. Astroarchaeology searches for the abandoned campfire, the lost tool, the derelict vessel. It looks for what experts call technosignatures, the material fingerprints of a technological civilization. A strange alloy on an asteroid, a geometric structure buried in lunar dust, an object orbiting where no natural one should be. These are the artifacts that would rewrite history. The philosophical seeds for this search were planted decades ago by thinkers like Carl Sagan, who pondered the profound silence of the cosmos. That silence is encapsulated in the famous Fermi paradox, which asks a simple, haunting question. If the universe is so vast and so old, where is everybody? The absence of obvious visitors has led to many theories, but astroarchaeology offers a direct, testable answer. Perhaps they were here and they left something behind. Or perhaps a probe from a distant star arrived millennia ago and has been silently drifting, a fossil from another world waiting to be recognized. This transforms our solar system from a collection of barren rocks into the ultimate cosmic attic, a place where ancient, forgotten things might have settled over billions of years. Think of Mars, a world that may have been habitable long before Earth. Think of the asteroid belt, a chaotic graveyard of primordial material from the solar system's violent birth. Think of the countless moons orbiting the gas giants, dark and icy, perfect for preserving something for eons. These are not just geological sites, they are potential archaeological dig sites on a planetary scale, and we are only now developing the tools to explore them properly. But what does an alien artifact actually look like? This is the prime directive of astroarchaeology, defining the very nature of our search. We are hunting for technosignatures, a term that simply means any physical object, structure, or substance that clearly betrays a non-natural technological origin. It is the difference between finding a strangely shaped rock and finding a perfectly crafted screw. In the vast silence of space, we are listening with our eyes, searching for the geometric shapes and unnatural materials that nature alone could never produce. Think of a probe, its surface a flawless metallic sphere, caught in a slow, eternal dance around the rings of Saturn. It would stand out against the chaotic beauty of the cosmos like a diamond in a gravel pit. Or picture a monolith, a rectangular slab of unknown material, half buried in the grey dust of the lunar surface, waiting for the sunrise to cast a long, artificial shadow. These objects would not need to be flashing with lights or broadcasting signals. Their mere existence, their form and composition, would be the message. Another haunting possibility is a derelict spacecraft, its engines cold and dark for eons, tumbling silently through the asteroid belt. It would be a fossil of a journey, a ghost ship from a star we have never seen. Even on a planetary surface, we might find structures that defy all geological explanation. Perhaps a series of formations on Mars align with a precision that erosion could never create, or a pattern in the ice of Europa suggests foundations rather than fractures. The key is to understand that we are not necessarily looking for a bustling alien city or a working outpost. We are searching for the silent, ancient, and likely malfunctioning remnants of a visitor's passage. These artifacts could be millions, even billions of years old, weathered by cosmic radiation and micrometeorite impacts until they are barely recognizable. They would be the ultimate cold case, a piece of evidence left behind from a crime scene where the only crime was curiosity. Finding one would not tell us where the builders are today. It would tell us only that they were here once and that we are not the first to look up at the stars and wonder. The universe has had plenty of time to leave its mark here. Our solar system is not a static snapshot. It is a living museum with a collection that spans 4.5 billion years. To understand the possibility of alien artifacts, we must first grapple with this scale, a concept scientists call deep time. 4.5 billion years is an almost incomprehensible span, a timeline so vast that every mountain range on Earth has risen and eroded away multiple times over. Within that ocean of time, the entire recorded history of humanity is less than a single drop. This deep time is the archaeologist's greatest ally. It means that even if an advanced civilization from a nearby star sent a probe on a one-way journey at a fraction of light speed, it could have arrived here hundreds of millions, even billions of years ago. They may have come and gone during the age of the dinosaurs, their visit leaving only a subtle, enduring trace in the geological record. This leads us to a fascinating and ancient idea known as panspermia. This is the hypothesis that life itself, in its most basic microbial form, could be distributed across the galaxy by asteroids, comets, or even deliberate seeding. In the context of astroarchaeology, this concept expands. What if the artifacts we seek are not gleaming metal probes but biological ones? We could be searching for ancient, fossilized microorganisms of extraterrestrial origin, preserved perfectly in the Martian permafrost or in the amber-like ice of a distant moon. Or perhaps the artifact is a technological seed, a tiny, resilient capsule designed to survive an eon-long journey and activate under the right conditions. A cosmic message in a bottle written in biology and engineering. This perspective fundamentally changes how we see our neighborhood. The solar system is not an empty void between planets. It is a vast, layered archaeological dig site where the strata are not made of rock and soil alone, but of vacuum, radiation, and eternal cold. An object left on the airless moon a billion years ago would not weather like a temple on Earth. It would be sandblasted by micrometeorites and bathed in cosmic rays, but it would not rust, rot, or be buried by shifting continents. It would sit in a state of near-perfect preservation, a time capsule waiting on a silent, grey shelf. Evidence could be entombed within the icy crust of Europa, shielded from radiation for eons. It could be buried deep within a carbon-rich asteroid, a hidden passenger on a rock that has wandered the solar system since its formation. The challenge is no longer believing such things could exist. The challenge and the thrilling mission of astroarchaeology is knowing where to look in a museum that spans billions of miles and billions of years. Our own moon is ground zero for this new kind of archaeology. It hangs in our sky not just as a companion world, but as a pristine museum, a silent archive where the past is not buried but displayed on the surface. The Moon's value lies in its profound inactivity. It has no atmosphere to cause erosion, no wind or rain to wear down structures. It has no active geology, no volcanoes or shifting tectonic plates to swallow evidence. An object that landed on the lunar surface 3 billion years ago would still be sitting exactly where it fell, patiently waiting under a blanket of dust. This makes the Moon the solar system's ultimate attic, a place where nothing is ever truly thrown away. This perfect preservation has already led to tantalizing mysteries. For decades, amateur and professional observers have pointed to lunar anomalies, strange features that defy easy explanation. There is the so-called Shackleton Pyramid, a strikingly angular formation near the Moon's south pole that stands out against the natural chaos of the terrain. There are unusual crater chains and alignments that some researchers suggest warrant a second, closer look. While most of these are almost certainly natural formations, shaped by ancient impacts and strange lighting, they highlight a crucial point. We have barely begun to examine our closest neighbor with the tools of an archaeologist. We have mapped it, but we have not truly searched it. Future missions will change that. The next wave of lunar exploration will not just be about planting flags or collecting rocks. It will be about systematic, intelligent prospecting. Imagine fleets of orbital satellites equipped with sensors far beyond simple cameras. These scanners would use ground-penetrating radar to peer meters below the dusty regolith, searching for metallic densities or hollow spaces. They would employ hyperspectral imagers to analyze the chemical composition of every square mile, flagging alloys or materials that have no business being there. On the surface, the work would fall to teams of autonomous rovers guided by sophisticated artificial intelligence. These would not be the solitary, cautious robots of the past. They would be agile scouts communicating with each other to investigate anomalies flagged from orbit. One rover might use a laser spectrometer to analyze a strange boulder, while another drills a small core sample nearby. Their prime targets would be the permanently shadowed craters at the lunar poles, places where sunlight never reaches and temperatures hover near absolute zero. These are natural deep freezes, potentially preserving not just water ice, but any organic or technological material for billions of years in perfect stasis. A core drill here could bring up a sample containing the ultimate discovery, a fragment of something not from Earth and not from the Moon, preserved in ice as clear as glass. The Moon, therefore, is not just a stepping stone to the stars. It is our first and most accessible dig site, a practice ground for the techniques we will need to search the rest of the solar system. If we cannot find evidence there with all our technological might, it will tell us one story. But if we do, it will mean the artifact was waiting for us all along, right in our own celestial backyard, a silent neighbor with an unimaginable tale. Mars stands as the solar system's greatest monument to what might have been. A second Earth in its youth, with flowing rivers, deep lakes, and a thick atmosphere, it represents a profound cosmic parallel. For any civilization charting the stars from a nearby system, our solar system would have presented a stunning sight, twin worlds of blue and red, both holding the potential for life. This makes Mars not just a geological curiosity, but a prime archaeological target. If interstellar travelers ever passed through our neighborhood, the red planet with its ancient habitable past would have been an irresistible destination for study, a base or a waypoint. The search there is not for living cities, but for the faded footprints of visitors who may have walked its rust-colored plains billions of years before the first microbes stirred on Earth. This quest is fueled by enduring mysteries that, while almost certainly natural, have captivated the human imagination for decades. The most famous is the so-called face on Mars, a mountain in the Cydonia region that, under specific lighting and low resolution, bore a startling resemblance to a humanoid visage. Nearby, formations like the D and M pyramid presented strange, angular geometry, while subsequent high-resolution imagery revealed these to be spectacular examples of pareidolia, our brain's tendency to see patterns in randomness. They performed an invaluable service. They highlighted a fundamental truth that our eyes and our curiosity are the first tools in this search. These features are not evidence, but they are powerful motivation. They tell us where to look more closely, to train our most advanced instruments on the landscapes that whisper of something more. The future of Martian archaeology will not rely on grainy photos, but on a new generation of robotic explorers equipped with senses far beyond our own. Picture autonomous rovers not much larger than a backpack, armed with ground-penetrating radar that can map underground chambers or buried metallic objects dozens of feet below the surface. They would carry molecular spectrometers, devices that can zap a rock with a laser and instantly read its chemical signature, searching for alloys or synthetic compounds that have no business forming in the Martian crust. A rover might pause by an ancient, dry riverbed, a place where water once carried and deposited material from across the planet. Its laser fires and the readout shows something impossible, a crystal lattice or a metal purity that nature could never achieve. That single fragment, cradled in a robotic arm, would be more than a rock. It would be a relic, a lost piece of a puzzle from across the stars, the first physical proof placed directly in our hands that we are not, and never have been, alone in this vast universe. Beyond Mars lies a realm of chaos and opportunity, the asteroid belt. This vast donut of rocky debris between Mars and Jupiter is often pictured as a crowded, dangerous place, but in reality its members are scattered over millions of miles of empty space. For an astro-archaeologist, this is not a barrier, it is a promise. These asteroids are the primordial leftovers from the solar system's violent birth, the unused building materials that never formed a planet. They are time capsules preserving the original chemistry of our cosmic neighborhood from over 4 billion years ago. But what if among these ancient rocks there is a piece of something far older and far stranger, a visitor that got stuck here? The concept is startlingly plausible. We now know that interstellar objects like the mysterious Oumuamua pass through our inner solar system with some regularity. Most speed through and are gone forever, but what if one, long ago, was snared by the gentle gravity of a large asteroid or captured into a stable orbit around the Sun? An ancient probe, its mission long over, could be tumbling silently among these mountains of stone, indistinguishable from a distance but holding a secret of cosmic origins. This transforms the asteroid belt from a mere collection of rocks into the ultimate cosmic junkyard, a place where anything lost or abandoned over the eons might eventually come to rest. The very corporations that will one day mine these asteroids for precious metals and water could become the unlikely pioneers of this new archaeology. Picture a mining outpost on Ceres, the belt's largest dwarf planet. A survey drone tasked with scanning a promising metallic asteroid sends back its data. The spectral analysis, which reads the unique light signature of materials, shows something impossible. The asteroid's surface is not just rich in iron and nickel. It is composed of an alloy of a purity and crystalline structure that defies all known metallurgy. It is a metal that should not exist, arranged in a pattern that screams of intelligent design. The drone moves closer, its cameras revealing geometric patterns etched into the rock, patterns that align with the asteroid's spin axis in a way natural forces never could. What began as a routine commercial scan has just become the discovery of the millennium. The mining operation halts, and the site is immediately placed under the highest scientific quarantine. Robotic arms, guided by the most careful programmers on Earth, would attempt to extract a sample not for profit but for proof. This scenario highlights a profound truth. The greatest discovery in human history may not be made by a government space agency on a flagship mission, but by a commercial prospector running a standard scan. The asteroid belt, therefore, represents a dual frontier. It is a source of material wealth that will fuel our expansion into the solar system, and it is potentially the richest archaeological site of all, a drifting graveyard where a single strange fragment could tell us we have been sharing our solar system with ghosts from other stars for longer than life has walked the Earth. The search for artifacts must also plunge into the deepest cold, to the frozen moons orbiting the gas giants. Jupiter's Europa and Saturn's Enceladus are worlds encased in miles of ice, hiding vast, dark, salty oceans that may hold more water than all of Earth's seas combined. For any civilization charting the galaxy, these are not just frozen rocks. They are biological treasure chests, rare and precious environments where the chemistry for life might be simmering in the eternal dark. This presents a compelling hypothesis. If an ancient interstellar culture was motivated by science, or perhaps by a desire to cultivate life, these subsurface oceans would be irresistible targets. They would not build cities on the surface. They would place delicate, sophisticated instruments directly at the source. Imagine a probe, slender and resilient, designed to melt its way through the ice shell and descend into the alien sea below. Its mission could have been observation, to study a nascent biosphere over millions of years. Or its purpose could have been more profound, to gently introduce the building blocks of life, a silent gardener tending a cosmic seed. After fulfilling its purpose, such a probe might have returned to a dormant state, anchoring itself to the underside of the ice shelf or settling on the abyssal seafloor. There it would wait, a frozen sentinel in a world of liquid water, preserved perfectly in the constant, frigid dark. This is where our own quest for life collides directly with the search for intelligence. The very missions we are planning to find microbes on Europa could instead find the machine that put them there. Picture a future cryobot, a torpedo-shaped melter probe funded by Earth agencies, slowly descending through Europa's icy crust. Its sensors are tuned for organic molecules and strange microbial shapes, but as it breaches into the open ocean, its sonar paints a startling image. Nestled against a hydrothermal vent on the seafloor is an object of perfect geometric symmetry, a smooth ellipsoid untouched by the mineral deposits that coat everything else. The cryobot's lights illuminate a surface of unfamiliar, non-corroding metal. This would be the ultimate cosmic irony and the ultimate discovery. We would have found life, but not as we expected. We would have found the gardener, not the garden. The implications would unravel everything. It would mean biology on Earth and perhaps across the galaxy is not a solitary accident but part of a shared, cultivated heritage. It would mean the universe is not just habitable but inhabited by minds that cared enough to plant seeds in the dark. Our search for our own origins would suddenly become a search for our creators, and every icy moon in the outer solar system would transform from a scientific target into a hallowed archaeological site, holding secrets in the deep, cold silence. Far beyond the last of the giant planets lies the true frontier, a realm of perpetual twilight and deep freeze. The Kuiper belt and the vast spherical Oort cloud are not empty voids, but the solar system's ultimate attic, filled with trillions of icy relics from our own formation. These regions are so distant and so cold that time itself seems to slow to a crawl. An object drifting here has remained almost unchanged for billions of years, preserved in the perfect stasis of near absolute zero. This makes them not just scientific curiosities, but perhaps the ideal long-term parking lot for something that did not originate here. If an ancient interstellar traveler wanted to hide in plain sight, to observe a star system from a quiet, dark distance for eons, this is where it would go. The very nature of these zones transforms our search. We are no longer looking just on planetary surfaces, but into a diffuse cloud of potential hiding places, each a dark, silent world of ice and rock. This concept is captured by the theoretical Bracewell probe, named for the scientist who first seriously proposed it. Imagine a fully autonomous machine built by a civilization long gone, programmed with a simple, patient mission. It enters a promising star system, finds a stable orbit in its frozen outskirts, and powers down into a state of near-total hibernation. For millennia, it does nothing but listen and record. Then, only when it detects the unmistakable technosignatures of an emerging civilization, like our radio broadcasts or first rocket launches, it stirs from its slumber. It might attempt a cautious, pre-programmed communication, or simply begin transmitting its stored data back to its point of origin, a message saying life is here. Such a probe would be the ultimate astro-archaeological find, a functioning artifact rather than a derelict. It would not be a silent monument but a teacher. Finding one would be like discovering a library where the books can read themselves aloud. The practical hunt in this unimaginable darkness begins not with rockets but with light. The first missions to search these frontiers will use the most powerful long-range telescopes we can build, equipped with adaptive optics to cancel out the blurring of Earth's atmosphere. They will not simply map large objects, they will perform a detailed spectral census looking for anomalies. An object with a highly unusual albedo, reflecting light in a pattern no known ice or rock would be flagged immediately. More intriguing would be an object with a strange thermal signature, emitting a faint, persistent warmth that the distant sun could not possibly provide, hinting at an internal power source long thought dormant. A single, tiny pinprick of anomalous heat in that all-consuming cold would be a beacon. The discovery protocol for such a find would be unlike any other. We could not send a quick reconnaissance mission. The distances are too vast, the travel times measured in decades. Instead, every instrument at our disposal would be focused on that one point of data. We would analyze its orbit with extreme precision. Is it bound to the sun or on a path that suggests an interstellar origin? We would attempt every form of passive and active sensing, bathing it in radar and listening across every frequency for even the faintest whisper of a signal. The ultimate patient goal might be to dispatch an interstellar probe of our own, a vessel designed to spend a human lifetime coasting toward that distant speck for a close-up view. That journey itself would become a new kind of archaeology, a multi-generational expedition to finally meet the silent watcher in the dark and learn if it has been waiting for us all along. These silent sentinels will not be found by eyes alone. They will be uncovered by a new toolkit, a suite of sensors and scanners designed to see what nature hides. The astroarchaeologist of the future carries instruments that make today's technology look like simple magnifying glasses. In orbit, the first line of detection will be synthetic aperture radar, or SAR. This is not a simple camera. By bouncing radio waves off a planet's surface and measuring their return, it can create incredibly detailed three-dimensional maps, seeing through surface dust and even penetrating several meters into loose soil. A perfectly smooth metallic sphere buried under the red sands of Mars would stand out in a SAR image like a coin under a thin blanket, its unnatural geometry screaming against the chaotic terrain. Complementing this will be hyperspectral imagers. Where our eyes see only color, these instruments see the unique chemical fingerprint of every material. From hundreds of miles up, they can scan a cliff face or a crater floor and instantly determine its composition, distinguishing between basalt, iron oxide, or something far more exotic. They would flag the presence of alloys or crystalline structures with a purity that natural geologic processes cannot achieve, painting a target on any patch of ground that simply does not belong. To peer even deeper, future missions may employ quantum gravimeters. These exquisitely sensitive devices measure tiny variations in a planet's gravitational field. A large, dense metallic object buried deep beneath the surface, like a massive engine core or a collapsed structure, would create a minute but detectable gravitational anomaly, a hidden heaviness that betrays its presence. Some proposed tools sound like pure science fiction, yet are grounded in real physics. Consider the neutrino detector. These ghostly particles pass through almost all matter effortlessly. But a sufficiently large and dense artificial object, perhaps a derelict ship's power core, would cast a subtle shadow in a neutrino stream passing through a planet. Detecting that shadow would be like finding a hidden chamber by watching how light bends around it, a revelation of something massive and unnatural hiding in plain sight. Yet all these magnificent machines would generate an avalanche of data, an endless digital landscape where the needle in the haystack is a single pixel with a story to tell. This is where artificial intelligence becomes the indispensable partner. We will train neural networks not just to recognize rocks and craters, but to develop a sense of cosmic strangeness. They will be fed millions of orbital and surface images, learning every nuance of natural geology. Their sole purpose will be to spot the outlier, the one in a billion anomaly that defies the pattern. A straight line on an otherwise fractured landscape, a shadow with angles too sharp, a thermal emission in the dead of a lunar night with no sun to cause it. The eye does not get tired, does not suffer from pareidolia, and does not overlook a detail at the end of a long shift. It sifts the endless noise, presenting a human operator with only a handful of tantalizing possibilities, each with a probability score attached. This transforms the search from a hopeful glance to a systematic excavation of data, turning petabytes of information into a single, glowing waypoint on a map, a place where the dig must begin. The silent, patient diggers of this new frontier will not be human. They will be armies of autonomous machines, tireless and precise, designed for worlds where a single misstep could erase a billion-year-old clue. Picture a cave entrance on Mars, a dark maw in a rust-colored cliff face. Instead of a solitary rover cautiously peering inside, a cloud of insect-sized drones descends. They are a swarm, each no larger than your hand, equipped with tiny LiDAR lasers and cameras. They flow into the darkness like intelligent dust, their collective artificial intelligence mapping every stalactite and crevice in 3 dimensions, sharing data instantly to build a complete model of the cavern. One drone, its sensors detecting an unusual thermal signature from a side passage, signals the swarm. A subgroup peels off to investigate, floating toward a heat source that no geothermal activity should explain. This is collaborative autonomy in action, robots working as a unified, thinking organism, capable of exploring places far too dangerous or delicate for any single machine. On the lunar surface, the excavation takes a different form. A team of dog-sized rovers, their bodies agile and low to the ground, approaches a flagged anomaly. Their movements are eerily coordinated, not through remote control from Earth, but through a shared situational awareness. One rover extends a delicate manipulator arm, brushing away the fine gray dust with puffs of inert gas. Another uses ground-penetrating radar to see what lies beneath, painting a real-time image for the whole team. A third, equipped with a core drill, waits for the signal. When the radar reveals a dense, metallic object just 10 centimeters down, the drilling rover moves in with surgeon's precision. It does not need to wait 20 minutes for instructions from mission control. Its onboard eye analyzes the radar data, calculates the optimal drill angle to avoid damaging the artifact, and begins the extraction autonomously. The humans are looped in, watching a live stream of discovery, but the critical decisions happen in the moment on the ground by the machines that are there. For targets buried deeper, the tools become even more specialized. Imagine micro-burrowing probes, slender devices that look like mechanical earthworms. They are designed not to dig massive trenches, but to navigate through the loose regolith like a needle through fabric. One might be deployed at the edge of a curious debris field. It vibrates gently, using a peristaltic motion to sink straight down, carrying a tiny suite of sensors. As it descends, it performs a continuous chemical analysis of each layer it passes through, creating a vertical timeline of the site. Suddenly, its path of least resistance shifts. It has encountered not more loose soil, but a smooth, solid barrier. The probe adjusts, moving laterally along the object's surface, mapping its contours from below. It has found not a rock, but something buried intentionally, something that interrupted the natural settling of dust over millennia. This hands-off, minimally invasive approach is the golden rule of off-world archaeology. The goal is to uncover evidence without contamination, to study without destroying, and these robotic swarms and probes are the perfect field scientists. They work without fatigue, without bias, and without the breath that could fog a priceless view into the cosmos. They are our senses and our hands across the vast, silent dig sites of the solar system, turning data into discovery, one precise, autonomous movement at a time. Retrieving an artifact is only the beginning of the true challenge. The moment we bring a potential alien object into proximity with our own technology, or worse, back to Earth, we risk a catastrophic failure of science. We could contaminate it with our own bacteria, erasing its original biological signatures forever. Or we could accidentally trigger a dormant mechanism, damaging the artifact or ourselves. The solution will not be a laboratory on Earth, but a fortress of isolation in space, a dedicated orbital forensics facility where the rules of engagement are written in paranoia and precision. This would be a spacecraft unlike any other, designed not for travel but for absolute containment. Imagine a series of nested chambers like a Russian doll built for the most dangerous guest imaginable. The artifact, secured within its original sample container, would be docked to the outermost port. From there, robotic arms operating in a perfect vacuum would transfer it through multiple decontamination airlocks, each sealed with plasma fields and blistering heat designed to annihilate any terrestrial microbe. The final chamber would be its permanent home, a sterile vault where it floats in microgravity, untouched by human hands for all time. The scientists who study it would never be in the same room. They would work from separate modules, their observations conducted through a suite of tools that make today's microscopes seem primitive. One of the most powerful would be the femtosecond laser. This device uses pulses of light so brief they are measured in quadrillionths of a second. By firing these pulses at the artifact's surface, it can vaporize a layer of material just a few atoms thick, which is then analyzed by a mass spectrometer. This process, called laser ablation, creates an atom-by-atom map of the object's exterior composition without generating heat that could alter its structure. It could reveal the isotopic ratios of its metals, telling us if they were forged in a star we recognize or one from another galaxy entirely. To see inside without cutting it open, engineers might employ a quantum entanglement scanner. This technology, still in its theoretical infancy, would use pairs of entangled particles. One particle would be sent into the artifact while its twin remains in the sensor. Changes to the internal particle would be reflected instantaneously in its partner, allowing the team to build a three-dimensional image of internal components, cavities, or even circuitry with zero physical intrusion. It would be like developing X-ray vision that leaves no trace. The most cautious tool of all might be the molecular assembler. If a tiny nanogram sample is deemed safe to extract, this device would not just study it, it would recreate it. Using the atomic blueprint gathered from the lasers and scanners, the assembler would painstakingly construct a perfect duplicate of the sample, atom by atom, from a stock of base elements. This replica could then be subjected to destructive testing, heated, pressurized, or broken apart to understand its properties, while the original remains pristine and untouched in its vault. Every protocol used for Apollo's lunar samples would be considered recklessly lax here. The guiding principle is planetary protection in reverse. We are not protecting other worlds from our contamination. We are protecting the artifact, and by extension ourselves, from an unknown exchange. Every bolt, every sensor, every breath of air in the facility would be monitored. The data streams back to Earth would be the only physical connection, a torrent of information that must answer the ultimate question before any closer contact is ever considered. Is this a silent piece of history, or does it have a purpose we have not yet awakened? The artifact sits in its sterile vault, a riddle wrapped in unknown physics. Decrypting its purpose may be a greater challenge than finding it. We are not just archaeologists now, we are cryptographers faced with a message written in the language of engineering by a mind we cannot fathom. The first and most daunting question is one of interface. Would a civilization millions of years more advanced build something intended for others to find, with obvious controls or displays? Or is their technology so seamlessly integrated, so organically functional, that it has no buttons or screens as we know them? The artifact might appear as a smooth, featureless obelisk, its functions activated by thought, touch, or conditions we cannot replicate. Our instinct to probe it with physical tools might be as crude as a caveman trying to operate a smartphone by licking it. This forces us to consider the foundation of all technology, physics itself. Is their engineering based on the same universal constants we observe? Do they utilize dimensions of space we cannot perceive, or states of matter that exist only under conditions we cannot create? An object might function perfectly under the gravitational pull of its home world, or draw power from a background energy field invisible to our instruments. It could be dormant not because it is broken, but because the trigger for its awakening is something as simple as a specific neutrino flux or the magnetic song of a pulsar we have not yet listened for. To navigate this labyrinth, we would turn to our most powerful tool for understanding complexity, artificial intelligence. We would feed the AI every scrap of data from the orbital scans, the femtosecond laser maps, and the quantum entanglement imagery. Its task would not be to give us an answer, but to run a universe of simulations. It would model countless interaction scenarios, testing theoretical physics models against the object's observed properties. What happens if we expose it to a concentrated beam of muons? How does its thermal signature change when bathed in the resonant frequency of the hydrogen line? The AI would be our infinite patient lab assistant, running millions of virtual experiments to find the one combination that elicites a response, all without ever touching the precious original. Alongside this brute force computational approach, a more delicate science would emerge, a new field we might call xenolinguistics. This is not merely the search for alien writing, but the search for any structured information, any pattern that encodes meaning. Teams would analyze the artifact's surface geometry, searching for ratios that match mathematical constants like pi or the fine structure constant, universal concepts any technological species would know. They would look for sequences in molecular arrangements or rhythmic pulses in minute energy emissions. The ultimate hope is that the builders embedded a primer, a kind of cosmic Rosetta Stone that begins with simple mathematics and builds into more complex ideas. Finding that key would not just tell us what the artifact does, it would offer a fleeting glimpse into the architecture of an alien mind, revealing how they perceive logic, beauty, and perhaps even their place in the cosmos. The final, cautious step might be an attempt at activation. Using the AI's most promising simulations as a guide, we might try to provide a specific form of energy, not with a clumsy cable, but with precisely tuned lasers or magnetic fields projected across the sterile vault. The moment of success would not be a dramatic explosion of light and sound. It might be subtle, a change in the artifact's thermal profile, a harmonic vibration detected by seismometers, or a pattern of internal lights activating in a sequence that our eye recognizes as a prime number countdown. That response, however faint, would be the first conversation humanity ever had with intelligence from beyond our world. It would mean the artifact is not just a relic but a messenger, and we have finally learned how to say hello. The silence of the cosmos might not mean we are alone. It could mean we are late, Imagine a single, intelligent seed cast into the galaxy, not just to explore, but to multiply. This is the essence of the von Neumann probe, a concept that transforms astroarchaeology from a treasure hunt into a forensic investigation of a potential cosmic industrial revolution. Named for the visionary mathematician John von Neumann, the idea is starkly elegant. A single, self-replicating probe arrives in a star system rich in raw materials. It lands on an asteroid or a barren moon, and using advanced robotics and nanotechnology, it begins to disassemble the very ground beneath it. It mines metals, harvests silicon, and processes ice for water and fuel. Its sole purpose is to use these local resources to build perfect copies of itself. Once the first copy is complete, the original and its clone launch toward new star systems where the process repeats. Exponential growth takes over. From one probe you get two, from two, four, from four, 8. Within a few million years, a span that is a blink in cosmic time. A wave of such probes could saturate the entire Milky Way galaxy. The profound implication is that we should not be looking for a solitary artifact, but for the scattered evidence of a vast, automated, and possibly ancient industrial enterprise. The search shifts from finding the needle in the haystack to finding the haystack itself, or rather, the factory that made all the needles. What would the remnants of such a project look like after eons of dormancy? Astroarchaeologists would become cosmic detectives, scanning for anomalies that suggest not just a visitor, but a builder. A prime target would be certain asteroids or airless moons that show signs of inexplicable resource depletion. Imagine a spectral scan of a metallic asteroid that reveals a perfect geometric crater, as if a giant cookie cutter had removed a massive section of pure iron nickel ore, leaving behind unnaturally smooth walls. Or consider a moon whose surface is littered not with random impact debris, but with strangely standardized fragments like the discarded shavings and offcuts from a machining process. The most compelling evidence might be the factories themselves, now dark and silent. We could find structures of immense scale and stark geometry on otherwise featureless worlds. Picture a vast hexagonal latticework on the plains of Ceres, a framework designed to cradle asteroids as they were processed, now half buried in dust. Or a series of perfectly aligned boreholes on Mars, descending in a precise spiral pattern into the crust, far too orderly for any natural geothermal vent. These would not be artistic monuments, they would be utilitarian, brutalist architecture on a planetary scale, the fossilized machinery of a mind that saw solar systems as raw material and time as a tool. A malfunction in this network could leave behind even stranger clues. Perhaps a replicator suffered a programming error a billion years ago and began producing nonsensical variants, leaving a graveyard of bizarre, half-formed machine shapes scattered across a crater floor. Or maybe a probe's replication sequence was interrupted, leaving a partially constructed duplicate fused to the bedrock, a metallic skeleton caught forever in the act of being born. This scenario forces us to confront a humbling possibility. The greatest archaeological find in human history might not be a glorious starship or a communicating monolith. It might be a cosmic junkyard, the silent, rusting evidence that someone or something once undertook a project of such staggering ambition that it aimed to reshape the galaxy itself, one self-replicating machine at a time. And we might just be living in the quiet aftermath, walking among the dormant, forgotten machines of a builder who has already moved on. But what if the artifact is not a teacher, but a sentinel? The most chilling answer to the cosmic silence is a theory known as the Dark Forest. It proposes a universe where every civilization is a hunter, moving through the galactic undergrowth with infinite caution, terrified of revealing its location. In this grim cosmology, any beacon is a target, and any unknown contact is a threat to be eliminated preemptively. This theory casts a long, cold shadow over our entire search. That perfectly preserved probe, that geometric structure on a distant moon, might not be a gift or a relic of exploration. It could be a warning sign, a boundary marker, or something far more dangerous. Imagine a scenario where our orbital forensics facility, after years of study, finally deciphers a core function of the object. The AI simulations converge not on a communication protocol, but on a defensive subroutine. The artifact is not a recorder, it is a tripwire. Its purpose is not to observe emerging life, but to monitor for the specific technological signatures of a spacefaring civilization, the kind that could one day become a rival. Upon detection, its dormant programming awakens. Perhaps it emits a powerful, focused burst of data, a single pulse aimed at a point in deep space, a homing signal that says a potential competitor is here. Or worse, its function could be autonomous and local. It might be designed to neutralize the threat itself, using mechanisms we cannot yet comprehend. A burst of directed radiation to sterilize a planet's surface, a triggered gravitational anomaly to destabilize a star, a command that hijacks the very replicating von Neumann probes we discussed, turning a dormant industrial network into a berserker swarm aimed at its new host system. This possibility transforms astroarchaeology from a pure science into a discipline of profound caution. Every new protocol must be built around a single, paramount question: is it safe to wake this thing up? Threat assessment would become the first and most critical phase of study, long before any attempt at decryption or activation. This shifts the focus of our remote tools. Lasers and magnetic fields would not be used to say hello, but to very carefully gauge reactivity. Scientists would begin with the cosmic equivalent of tapping on a glass cage with a very long stick. They would expose the artifact to minute, carefully controlled energy patterns designed to mimic natural cosmic phenomena, watching for any deviation from passive response. Does the object's internal energy state fluctuate when bathed in the radio frequency signature of a fission reaction? Does its surface resonate when scanned with a pattern that matches primitive rocket exhaust? Any sign of active targeting or energy buildup would trigger an immediate and total quarantine. The entire facility might be programmed to enact a fail-safe, using magnetic containment fields or, as a last resort, a precisely timed kinetic impact to push the artifact into a solar disposal trajectory, sacrificing the find to protect the finders. This introduces an ethical dilemma of staggering scale. If the dark forest is real, then some cosmic ruins are not monuments, they are minefields. The greatest discovery in history could also be the last mistake we ever make. It forces us to ask a terrible question: is the silence of the stars a sign of emptiness or a sign of something hiding? And are we, in our eager search for answers, about to knock on the wrong door? A single confirmed artifact would not just change science, it would rewrite the human story in an instant. The initial announcement, verified beyond any reasonable doubt by every major space agency and academic institution on Earth, would trigger a global psychological event unlike any in history. For days, perhaps weeks, the normal rhythms of society would stutter. News cycles would collapse into a single, all-consuming topic. Social media would fracture between awe, existential dread, and rampant speculation. There would be a palpable, worldwide silence in the mind, a collective intake of breath as 8 billion people simultaneously looked up from their daily lives and grasped a new reality. We are not alone, and we never have been. The immediate aftermath would be a turbulent mix of profound unity and dangerous fracture. On one hand, the discovery could catalyze an unprecedented unification of scientific purpose. The old nationalistic rivalries of space exploration might dissolve overnight, seen suddenly as petty and provincial. A shared, species-wide mission would emerge, a coordinated effort to study the artifact, search for others, and decode the cosmic context we now know we inhabit. Funding for astronomy, physics, and xenolinguistics would skyrocket, supported by public demand and a new understanding that these are not abstract fields, but essential tools for our survival and growth. International collaborations previously bogged down in bureaucracy could form in months, driven by a simple, unifying question: what does this mean for all of us? Yet this optimistic view clashes with a darker, equally plausible outcome. The artifact and any technology it represents would be the ultimate strategic prize. Which nation or corporate entity controls the orbital forensics facility? Who interprets the data first? The potential for a geopolitical scramble, a new Cold War fought not with ideologies but over access to alien science, is terrifyingly real. Secrecy and espionage would infect the research. Nations might race to launch their own retrieval missions to other potential sites, turning the solar system into a competitive frontier rather than a shared heritage. The artifact could become a wedge, not a bridge, amplifying our tribal instincts on a cosmic stage. Philosophically and religiously, the tremors would be deep and lasting. Every creation myth, every theological framework placing humanity at the center of a divine narrative would face a profound challenge. Some faiths might adapt, viewing the builders as another part of a grand creation. Others might experience crisis, as the unique status of humanity in the cosmos is irrevocably shattered. New spiritual movements would likely arise, centered on cosmic unity or the worship of these ancient, advanced builders as de facto gods. The very question, what does it mean to be human, would gain a new comparative dimension. We are no longer the sole measure of intelligence, creativity, or destiny. We are a young species, perhaps a naive one, in a galaxy that has been busy with thought for billions of years before we existed. This shift in perspective from pinnacle to participant could be the healthiest dose of humility we have ever received. It might ignite a new age of exploration, not just outward but inward. Our art, our literature, our very drive to understand our place would be reinvigorated with a new cosmic context. Conversely, it could breed a cosmic isolationism, a fear that drives us to hide, to turn inward and fortify our planet, seeing the universe not as a frontier but as a forest full of unseen eyes. The artifact's greatest lesson may have nothing to do with its function. Its mere existence is the message, a mirror held up to our civilization, revealing whether we are mature enough to handle the truth that we are not the only children in this vast, ancient house. The discovery of an alien artifact would immediately trigger a crisis no one is prepared for, a legal and ethical vacuum with the fate of a cosmic treasure hanging in the balance. Our current framework for governing space is a relic of the Cold War, centered on the 1967 Outer Space Treaty. Its core principles are noble, stating that space is the province of all mankind, not subject to national appropriation by claim of sovereignty. But this treaty was written for flags and footprints, not for deciphering a billion-year-old machine. It completely fails to address the fundamental question: who owns something that was never ours to begin with? The moment a rover's claw closes around a strange metallic fragment, a storm of competing claims would erupt. The nation or private company that financed the mission would argue their hardware made the discovery, granting them rights. The international scientific community would insist such a find is a heritage of all humanity, beyond any one entity's control. And what of the builders themselves? Do their rights, however distant or extinct, factor into our law? This is not an abstract debate. It is a recipe for conflict that could shatter global cooperation just when we need it most. The stakes are not just about prestige, but about power and profit. Any technology derived from studying the artifact, from new materials to revolutionary physics, could be worth incalculable wealth. Would that knowledge be patented by a corporation and sold to the highest bidder, creating a monopoly on alien science? Or would it be released openly, a gift to accelerate all human progress? The legal ambiguity invites a cosmic gold rush, a scramble where the first to grab dictates the terms for everyone else. A nation could land next to a discovered site and declare a security perimeter, effectively claiming it through presence and force, twisting the treaty's peaceful use clause into a justification for control. A mining conglomerate could argue that an artifact embedded in an asteroid is simply part of the mineral claim they already own, turning a sacred relic into a commodity to be processed. To prevent this descent into chaos, we must build the legal framework now before the discovery is made. Humanity needs a new covenant, something we might call a Galactic Heritage Act. This would be an international treaty negotiated with unprecedented unity, establishing clear rules for a scenario we all hope to face. Its first principle must be that any non-human artifact is the common heritage of humanity, inalienable and incapable of being owned by any state, corporation, or individual. It would mandate that any find be placed under the stewardship of a specially formed international scientific body, with representation from across our world's cultures and disciplines. This body would manage all research, ensuring transparency and equitable sharing of all non-dangerous data. The treaty would strictly prohibit the weaponization of any derived technology and create binding protocols for containment and study that prioritize safety over speed or profit. Most importantly, it would outline a path for benefit sharing. Any technological advancements that improve life on Earth, from medical breakthroughs to new energy sources, would be licensed under terms that fund further exploration and uplift all nations, not just the wealthy ones who reached it first. Crafting such a treaty would be the most difficult diplomatic endeavor in history, requiring us to set aside terrestrial rivalries and think as a single species with a shared cosmic destiny. But the alternative is unthinkable: to stand at the threshold of our greatest understanding and let it fracture us over ancient quarrels. By writing these rules in a time of calm hope, we ensure that if we ever find a message from the stars, our first reply is not an argument over who gets to open it, but a unified, peaceful, and curious welcome from the whole of planet Earth. The final frontier will not be explored by scientists alone. This grand search for cosmic artifacts will be a shared human endeavor, powered by the curiosity of millions. The key lies in a revolution already underway: citizen science. Imagine a platform where, after your evening coffee, you log on not to social media, but to a portal streaming raw, high-resolution images from a rover on Mars. Your task is simple: scan the terrain. You are not a trained geologist, but your human brain is a peerless pattern recognition machine, capable of spotting the one odd shadow, the one unnatural straight line in a landscape of chaos that an algorithm might dismiss. With a click, you flag it for review. The next day, you might receive an alert: your anomaly has been elevated for closer study by the mission team. You have just become part of the discovery chain, a cosmic detective from your living room. This is not a distant dream. Projects like this already exist for classifying galaxies and tracking asteroids. The search for artifacts will scale this to an unprecedented level, creating a global network of observers, a distributed consciousness sifting the sands of other worlds. To make this tangible, educational programs will immerse students in virtual reality simulations. A class could strap on headsets and find themselves standing on the dusty plains of the moon, virtual tools in hand. Their assignment is to conduct a survey of a simulated dig site, using spectral analyzers and ground-penetrating radar to locate a buried artifact placed by the program. They learn the scientific method not from a textbook, but through their own hands, feeling the thrill of a potential find in an alien landscape. This gamified learning builds the next generation of astro-archaeologists and, more importantly, fosters a deep, personal connection to the cosmos. The public's role will extend beyond analysis to direct support. When a particularly promising anomaly is identified but falls outside official mission parameters, a crowdfunding campaign could launch. People from around the world could contribute small amounts to fund a dedicated microsatellite or a specialized rover scan. This democratizes the search, allowing the collective will of the curious to investigate leads that bureaucracies might deem too speculative. A community-funded probe named by its backers, journeying to examine a strange feature on Ceres, becomes a monument to shared human curiosity. This creates a powerful feedback loop. Public participation generates more data and interest, which fuels more sophisticated platforms and educational tools, which in turn draws more people into the fold. We will transition from a world where space exploration is something done for us by distant agencies to a civilization where it is something done by us together. The search for alien artifacts will cease to be an abstract scientific pursuit and become a unifying human project, a global community of cosmic explorers linked not by nationality, but by a shared, burning question hanging in the starry silence above us all. Our greatest strength in this search is also our greatest weakness, the human brain's desperate need to find patterns. This impulse, called pareidolia, is why we see a face in the clouds or a man in the moon. In the silent, grainy images beamed back from other worlds, this tendency runs wild, transforming mountains into monuments and shadows into structures. The history of space exploration is littered with these cosmic false alarms. Remember the face on Mars, a captivating hill that, under better light, revealed itself as just a hill. Or the Martian spiders, dark seasonal patterns caused by sublimating carbon dioxide ice that, from orbit, look eerily like sprawling arachnids. Each of these cases taught the same hard lesson: our eyes are eager storytellers but terrible scientists. This is why astro-archaeology cannot be a visual hunt alone. It must be a discipline of brutal, uncompromising rigor, where excitement is the enemy and skepticism is the first tool in the kit. The standard for proof is not a strange shape in a photograph. It must be a physical property that shatters all known natural law. An object's composition must tell a story its shape cannot. Imagine a metallic fragment recovered from an asteroid. Initial scans show a bizarre alloy. The real test comes with isotopic analysis, a process that measures the unique nuclear fingerprints of elements. Every corner of our solar system has a predictable isotopic recipe, a blend forged in our sun's nursery. If that fragment contains nickel-60, a radioactive isotope not found naturally in our system, or has ratios of tungsten to hafnium that point to formation around a different kind of star entirely, that is a technosignature. No geological process, no matter how violent, can manufacture that. It is a calling card from another forge. The proof could be even more stunningly intricate. Under an atomic force microscope, a seemingly smooth surface might reveal a landscape of perfect, repeating geometry. Not the chaotic crystals of a mineral, but the orderly logic of circuitry, with conductive pathways and insulating layers built at the nanometer scale. This is not a shape that looks manufactured, it is a function that is manufactured. Nature does not build transistors. It does not code information in binary layers within a crystal lattice. Finding such a structure would silence all but the most stubborn critics, because it points unequivocally to a mind that understood physics not just to exploit it but to command it. This relentless demand for impossible evidence is what separates a daydream from a discovery. It means dismissing 99.99% of anomalies, not with disappointment, but with disciplined respect for the sheer creative chaos of the cosmos. The solar system is weird enough on its own. Our job is to find the one thing that is weirder than nature could ever be. Only then, when every natural explanation has been exhausted, when the data points to a truth that reshapes reality, can we truly say we have found something. It is a slow, meticulous process, a cosmic detective refusing to close the case until the evidence is not just convincing, but incontrovertible. This is the solemn promise of astro-archaeology, to trade the thrilling rush of a maybe for the world-altering weight of a certainty. The interstellar object Oumuamua offered humanity a fleeting, tantalizing glimpse of a visitor from another star system. Discovered in 2017, it was a cosmic passerby, already speeding away as our telescopes caught it. Its brief appearance sparked intense debate, not because it was clearly artificial, but because it stubbornly refused to fit neatly into any natural category. Its shape, inferred from extreme brightness variations, suggested something elongated, perhaps like a cigar or a flattened pancake. Most puzzling was its acceleration as it departed the Sun, a slight but measurable push that could not be explained by gravity alone. The outgassing of gases, a typical cause for such motion in comets, left no visible trail of dust or gas for our instruments to detect. This single object, a silent speck of data against the dark, became a perfect test case for the astro-archaeological mindset. Instead of choosing sides in a debate between comet or alien probe, we can use it as a drill, a dress rehearsal for the day we find something truly inexplicable. The critical lesson of Oumuamua is not what it was, but how unprepared we were to learn the truth. We had one chance, a few weeks of observation, and then it was gone forever into the interstellar dark. Our instruments, though powerful, were passive and distant. We watched it leave, our questions unanswered. This scenario forces a vital question for future artifact hunters. What would we need to know, and what tools would we need to have ready to never let such an opportunity slip away again? To move from speculation to certainty, we would need a rapid response capability, a pre-positioned interceptor probe ready to launch at a moment's notice toward any future interstellar visitor. Mission concepts like Project Lyra have already explored the staggering engineering required to chase down an object like Oumuamua. The challenges are immense, requiring slingshot maneuvers around Jupiter or even the Sun to achieve the necessary velocity, and journey times lasting years or decades. But if such a mission were feasible, the payoff would be the ultimate forensic examination. Imagine a probe finally matching velocity with the mysterious object, closing in to just a few dozen meters. Its first and most crucial instrument would be a high-resolution LiDAR and radar mapper. This would not just take pictures, it would construct a precise three-dimensional model, finally revealing the true shape, ending the speculation about whether it was a cigar, a slab, or something else entirely. Is the surface pitted and irregular like a natural asteroid, or does it show facets, seams, or geometric patterns? Next, a suite of molecular and atomic spectrometers would fire lasers or X-rays at the surface, performing a chemical autopsy from a distance. They would search for the isotopic fingerprints that scream of another star system, and crucially, they would look for any signs of refined materials or alloys. Does the surface contain pure metals in unnatural combinations? Is there evidence of layered composites or crystalline structures organized with a purpose? Perhaps most telling would be a simple thermal camera. By mapping the heat distribution across the object as it tumbles, scientists could determine its density and internal structure. Is it a solid, monolithic rock, or does the heat flow suggest hollow spaces, internal compartments, or materials with unusual conductive properties? A natural rock conducts and radiates heat in predictable ways, an engineered object might not. Finally, a sensitive magnetometer would sweep the area, searching for any residual magnetic field, the fading ghost of a powered system long shut down. Had we been able to deploy such a probe to Oumuamua, the data returned would have settled the debate within hours. Either we would have a detailed catalogue of a fascinating new type of natural interstellar object, a treasure for planetary science, or we would have the first confirmed physical evidence that we are not the only builders in this galaxy. The silence following its departure is a mandate. We must build the tools and the will to get a closer look next time, because the next visitor might not be a puzzle. It might be a message, and we cannot afford to be left reading the footnote in a scientific paper when we could be holding the letter in our hands. The ultimate ambition is not to chase one mystery, but to illuminate the entire dark room. This is the long-term vision of astroarchaeology, a shift from reactive hunts to proactive, permanent observation. The goal is a solar system-wide survey, an integrated network that turns our entire celestial neighborhood into a continuously monitored archaeological zone. Think of it as building a cosmic inventory, a complete and dynamic baseline of what normal looks like across billions of miles. Only by knowing every rock, every orbit, and every quiet background hum can we instantly recognize the one thing that does not belong. The foundation of this network would be a constellation of specialized telescopes, not on Earth but stationed in strategic solar orbits. Freed from our atmosphere's blur, these sentinels would maintain a constant, vigilant watch. Their primary mission would be a repetitive, patient scan, comparing each new image of a region with decades of archived data. Their artificial intelligence would be trained to flag the subtlest changes, a new pinprick of light where none existed before in the asteroid belt, a temporary thermal bloom on the night side of a distant moon, or a reflective glint from a crater wall that was dark just one orbit prior. This system would automatically detect and track every object above a certain size, creating a living catalog of our solar system's population. Any interstellar visitor, like the next Oumuamua, would be spotted the moment it crossed the threshold, its trajectory calculated and its nature assessed long before it could slip away unseen. This orbital watch would be complemented by a mobile fleet, a swarm of autonomous survey probes dedicated to the asteroid belt and the Trojan clouds. These are not mining ships but cartographers and census takers. Each probe would be equipped with advanced spectrometers and radar, tasked with visiting and cataloging thousands of objects. They would not just map shape and size, they would record the precise chemical and isotopic fingerprint of each asteroid and minor planet. This vast database would be the ultimate reference library. If a century from now, a mining scout analyzes a metallic asteroid and finds its composition is a perfect match for one catalogued long ago, that is expected. But if the analysis reveals a completely new alloy or shows that the object's isotopic signature is alien to our solar system, the alert would sound across the network. The anomaly would not be a grainy photo, it would be a data point that violates the established inventory, a statistical impossibility demanding immediate investigation. Finally, this survey mentality must become standard protocol for all future exploration. Every lander sent to Mars, every orbiter dispatched to Jupiter, every hopper designed for Titan would carry a unified sensor package as part of its core payload. These standardized instruments would perform consistent, calibrated measurements wherever they go, feeding data back into the central network. A seismometer on the Moon records regular, faint moonquakes, establishing a background rhythm. If one day it detects a sharp, localized vibration with a harmonic signature unlike any natural impact, that anomaly is instantly cross-referenced with orbital imagery and thermal data from that same grid square. A spectrometer on a Europa surface probe measures the common chemistry of the ice, creating a baseline. If it later passes over a fissure and detects a complex organic polymer that should not form in that environment, the flag is raised. This turns every mission, regardless of its primary goal, into a node in the sensory web, contributing to a growing understanding of what is ordinary so we can recognize the extraordinary. Building this persistent, intelligent nervous system for the solar system is a project that would span generations. It is a commitment to seeing our home not as a collection of separate worlds, but as a single, interconnected site of potential discovery. The payoff would be a transformation in our relationship with the cosmos. We would no longer be passive inhabitants of a single planet, glancing nervously at the dark. We would become the stewards of a system, the attentive curators of a museum whose full collection we are only beginning to catalog. In this carefully monitored quiet, the slightest whisper from the past would be heard, and the long silence would finally begin to speak. The relentless pursuit of these cosmic artifacts will ignite a technological renaissance, one whose greatest gift may not be the discovery itself, but the tools we forge along the way. This quest is far more than a scientific endeavor. It is an economic engine, a challenge that will demand radical leaps in capability, and in doing so, spin off innovations that reshape life on Earth. The need to see the unseen will push artificial intelligence beyond its current limits. We are not talking about simple pattern recognition, but about an eye that can reason like a field archaeologist, synthesizing data from a dozen different sensor types to form a hypothesis about what lies beneath the Martian soil. This contextual intelligence, developed to interpret alien landscapes, will revolutionize fields like medical diagnostics, where a system could cross-reference genetic data, imaging scans, and patient history to identify diseases with a detective's intuition. The robots we send will need a new kind of autonomy. They must navigate treacherous, unknown terrain without a 20-minute delay for instructions from Earth, making split-second decisions to preserve a potential find. The advanced robotics and tactile feedback systems created for this delicate work will transform disaster response, allowing machines to sift through earthquake rubble with a surgeon's care to locate survivors, or to perform complex repairs in the deep ocean or inside active volcanoes. Even the simple act of getting there faster will spark a revolution. The dream of a rapid response interceptor, ready to launch at a moment's notice to chase an interstellar visitor, cannot rely on conventional chemical rockets. It will necessitate breakthroughs in propulsion, perhaps in advanced nuclear, thermal, or electric propulsion systems that provide sustained thrust for years. The research and engineering poured into these faster, more efficient engines will slash travel times throughout the solar system, making the movement of people and materials between worlds not just possible but practical, laying the groundwork for a true spacefaring economy. The search will also force us to master energy in hostile environments. Powering a robotic swarm in the permanent shadow of a lunar crater or a deep space monitoring outpost in the Kuiper belt will require ultra-efficient, durable energy systems. The advances in compact fusion, next-generation solar cells that work in faint sunlight, or radioisotope thermoelectric generators with unprecedented longevity will trickle down to Earth, providing clean, reliable power for remote communities and making our global energy grid more resilient. This technological cascade mirrors the legacy of the Apollo program, which gave us everything from cordless tools and water purification systems to modern computer microchips. The search for alien artifacts will be our next great catalyst, but on a far grander scale. It will birth entirely new industries centered on in space manufacturing, where asteroids are processed not just for precious metals, but for the materials needed to build our orbital research facilities. It will create a massive market for hyper-advanced remote sensing, with companies competing to build smaller, cheaper, and more powerful spectral imagers and radar units, technology that will then be used to monitor climate change, manage agriculture, and discover new mineral deposits on our own planet. The tidal wave of data from a solar system-wide survey will drive the creation of unimaginable data analysis platforms, pushing the boundaries of cloud computing and quantum data processing. Ultimately, this self-reinforcing cycle of challenge and innovation does more than just look for answers in the past. It builds the very infrastructure for our future. The technologies born from this search will make a sustained human presence in space not a fragile experiment, but a sophisticated, sustainable reality. We may search for silent builders from the stars, but in the process, we will become the builders we always hope to find, crafting a new chapter of human achievement with every tool we invent to uncover the old ones. The moment a rover's sensor pings with impossible data, a silent global clock starts ticking. Every step that follows is choreographed by a protocol not born of science fiction, but of sober international planning. The first rule is verification, and it is absolute. The initial team on the ground, or more accurately, in mission control, would immediately enact a communications blackout on that specific data stream. No tweet, no leak, no breath of a rumor can escape. Their sole job is to gather more data, using every instrument at their disposal to rule out a sensor malfunction, a software glitch, or a bizarre but natural formation. They would reposition the rover, take new scans from different angles, and use a secondary, completely independent instrument to analyze the same spot. If the anomaly persists, the encrypted, highest priority alert is sent. This is not a public email. It travels through dedicated, secure channels to a pre-designated list of global space agencies and a special office within the United Nations. The message is simple and coded. A potential Category 5 discovery has been made. This triggers the simultaneous activation of verification cells in laboratories across the world. Raw data packets are transmitted to independent teams in Europe, Asia, and the Americas. These scientists, working under strict non-disclosure agreements, have one task: to attempt to disprove the finding using their own models and expertise. They are not looking for confirmation. They are trying to find a flaw, an error, any possible natural explanation. Only if all these independent pathways fail, if every lab concludes that the object's properties are irreconcilable with known nature, does the discovery move from potential to credible. This painstaking, redundant process might take weeks or even months, a necessary delay to build an unassailable wall of evidence. During this tense period, a separate, parallel protocol engages, focused on the message to humanity. A committee of scientists, diplomats, linguists, and psychologists would convene, tasked with crafting the single most important announcement in human history. Their guiding principle is unified transparency. There would be no single nation taking credit, no corporation making the reveal. The plan is for a coordinated, simultaneous broadcast from multiple world leaders and the Secretary-General of the UN, followed immediately by a detailed, technical briefing from the lead scientists involved. The language is carefully chosen, factual but not cold, awe-inspiring but not terrifying. It would present what is known, what is not known, and the clear international plan for what happens next, emphasizing that this is a discovery for all of humanity, managed by a coalition of the world's best minds. The goal is to replace chaos with context, to channel the inevitable global shock into a shared sense of purpose and cautious wonder. This meticulous, step-by-step dance is our best hope for turning a moment of cosmic revelation into the beginning of a new chapter, not the end of our collective composure. It is the rehearsal for a day we all dream of, ensuring that if we find a message in the dark, our first reply is not a scream but a calm, unified, and thoughtful hello. But this search for ancient builders forces us to confront a far deeper question. Are we, in this grand cosmic story, the archaeologists or the artifacts? Our quest to find alien technology might one day reveal that we are the ones leaving the relics for others to find. Consider the Voyager probes, those golden records carrying whispers of Earth into the interstellar dark. They are our first fragile attempts at creating a technosignature, a message in a bottle cast upon an ocean of stars. In a billion years, long after human civilization has transformed or vanished, those silent craft might still be drifting. To another intelligence, discovering Voyager would be the ultimate astro-archaeological find, a primitive but deliberate artifact from a young species that once looked up and dared to say, "We are here." Our satellites, our abandoned lunar landers, even the faint radio and television signals leaking from our planet, these are the layers of our own technological stratum slowly accumulating in the solar system. We are already building the ruins of tomorrow. This perspective turns the entire search inward. Every time we scan a Martian plain or an asteroid surface for something that does not belong, we are implicitly defining what it means to belong. We are deciding, through the lens of our own science and culture, what qualifies as evidence of a mind. That search holds up a mirror, forcing us to see our own civilization not as the inevitable pinnacle of evolution, but as one possible expression of intelligence in a universe of limitless possibilities. It asks us what we are building today that might survive the eons. Will our legacy be a silent ring of orbital debris or something more profound, a beacon of curiosity and creativity that endures? Ultimately, the drive to find alien artifacts is not really about them. It is about us. It is the expression of a loneliness so deep it has become a kind of engine powering our telescopes and our dreams. We scan the infinite quiet not just for company but for context. Finding another's artifact would tell us we are not alone. But even in the searching, in the meticulous sifting of cosmic dust, we are answering a fundamental human need to understand our place in the story. Are we a unique opening chapter or a single sentence in an epic written across galaxies? The silence for now remains, but within it our curiosity echoes, a hopeful sound against the vast and patient dark. This journey began by redefining the very ground beneath our feet, or rather, the lack of it. We started with the core idea of astro-archaeology, a science that trades shovels for spectrometers and digs not in soil, but in the silent vacuum between worlds. We have explored the potential dig sites from the dusty, preserved plains of our moon to the icy, hidden oceans of Europa and the chaotic junkyard of the asteroid belt. We have equipped our robotic explorers with tools of astonishing sensitivity, from synthetic aperture radar that sees through rock to artificial intelligence that sifts cosmic noise for a single note of order. And we have confronted the staggering implications, the legal quandaries, the ethical minefields, and the sheer psychological weight of what finding a single artifact would mean for every person on this planet. This is not a flight of fancy, it is the logical, thrilling next step in our story as explorers. For millennia, humanity has looked to the dirt to understand who we are. Now we look to the stars for the same reason, blending our most ancient impulse to uncover the past with our most advanced machines. The search transforms the entire solar system from a collection of planets into a single, sprawling archaeological complex. Each crater a potential trench, each asteroid a possible relic. You are living at the dawn of this new age. The first surveyors are already in the field, the rovers and orbiters gathering the baseline data. The protocols are being written in laboratories and treaty halls. The great cosmic inventory is beginning. This means you are not just a spectator to history, you are a witness to its prologue. Your curiosity is the fuel for this endeavor. Support scientific literacy, follow the missions, gaze at the night sky with a new question. Do not see it as an empty black void. See it as the grandest museum of all, its collection illuminated by distant suns, its halls spanning billions of miles. A story is waiting in that dark, a narrative written in geometry and unknown alloys, a testament to minds that may have pondered the same silence. The dig has begun. The tools are poised, and the greatest discovery in history is out there, patiently waiting for us to learn